Hey guys, welcome back. This time around, we're going to begin our discussion on biochemistry. Biochemistry is the chemistry of biological functions. What's that mean? That means it's the study of all the chemical composition and all the physiological reactions that occur inside of a living organism. So it's going to make up all the structures that make me up, such as the skeleton and the muscles, but it's also going to be looking at the cellular level at the reactions that are occurring. Now, at the cellular level, we're going to find that water makes up about 68% of the overall volume of a cell. So most of the time, those reactions are occurring in a water-based environment. So frequently, biochemistry is known as wet chemistry. Now, there's two classes of compounds that are going to be found associated with biochemistry. Each class of compounds is actually a discipline in chemistry all to itself. One class of compounds is going to be the inorganic compounds. Inorganic compounds include water, salts, and many of our acids and our bases. Inorganic compounds can be ionically or covalently bonded. Inorganic compounds will not contain carbon, though. Inorganic compounds will not decay when we die. And the major roles of inorganic compounds is to give us our universal solvent in the form of water, but also to provide us our electrolytes so that we can have electrical currents, and to provide our acids and bases so we can regulate our proper pH in our body. Organic compounds, on the other hand, will always contain carbon, will always be covalently bonded, and typically are going to be quite bulky. Now, examples of organic compounds would be carbohydrates, fats, proteins, and nucleic acids. Now, they're going to be very essential to us in that they're going to be the foodstuffs, the building blocks that we're going to use to build larger structures in our body, such as cell membranes and tissues and organs. That set of reactions, that metabolic set of reactions, is known as anabolism or anabolic reactions. These will be the same organic molecules, though, that we will use to generate energy in our body by breaking them down. That set of metabolic reactions is known as catabolism or catabolic reactions. These molecules, that once I do die, will decay, they will rot. Now, when we're taking a look at the inorganic, that's where we'll start. The most abundant of all the inorganic is going to be water. It's going to represent 60 to 80% of the overall volume of living cells, and it's going to be a covalently bonded compound, if you recall. Now, since it represents 68% of the overall volume, that means it's going to be the compound in the highest concentration. That means that it is, by definition, the solvent. In fact, water is the universal solvent for all living organisms. That would make you think right off the bat that it's got some very unique properties that make it so in demand by all living organisms. Some of those properties include its high heat capacity. It's got the highest heat capacity of any molecule that we know of. What is heat capacity? It's the ability to absorb and redistribute large quantities of heat without a raise in body temperature. In fact, it can absorb and distribute so much heat that the way we measure heat, energy, is in the form of a calorie or a kilocalorie. And a kilocalorie, by definition, is the amount of heat required to raise 1 gram of water 1 degree C. Now, where do we see this played out? Well, think about it. If you're working and working out, or you're physically working outside, you're generating a lot of heat energy. And if you allow that heat energy to stay internally inside of your body, it would cause enzymatic reactions to stop functioning. So we have to have a way to redistribute that heat. And we use the blood, which is mostly made up of water. And we will distribute that heat to the surface of our skin, and we'll allow the heat to dissipate out, radiate out the surface of the skin. Now, there's times, though, that we're generating so much heat that just by allowing it to diffuse out or dissipate out at the surface skin won't be enough. We have to put something in motion to help push that effort forward a little bit more. And that second property associated with water is its heat of vaporization. Heat of vaporization is the amount of heat it takes to change a liquid to a gaseous state at boiling. It takes more heat energy to convert a gram of water at boiling from a liquid to a gaseous state than any other molecule. Now let's think how it plays out, because if we have all this generating all this heat at the blood level, obviously we become flush when we do that. And what that is doing is allowing the dilation of blood vessels to surface the skin. Dilation of blood vessels is bringing all that warmer blood to the surface. It's radiating out. If we can't radiate it out fast enough, then what we'll do is put drops of water on the surface of skin. Odds are the outside environment is going to be cooler than the inside environment. So that water feels a little cool on the surface of my skin. Well, now, if it's staying cool on the surface of the skin and I'm dragging heat out, it's going to drag heat out because heat will go from a place of warmer to cooler. It'll try to dissipate out and it will migrate out. And as it does, it actually is going to, large quantities of heat is going to be forced out before we can change that liquid droplet into a vapor state. Have you ever seen somebody vaporize water? Well, one of my idols when I was a kid was a man by the name of Reggie White. Reggie White was a defensive tackle for the University of Tennessee. He went on to play for the Philadelphia Eagles as well as the Green Bay. Now, I really remember him at the Green Bay Packers. Reggie had a bald head. He was a work hard kind of athlete. But in Green Bay, it can get quite cold in the wintertime. And Reggie would be working hard on defense, and he'd come out and sit on the bench, and he'd take his helmet off, and I'd see the steam coming off the top of his head, his bald head, and I'm going, wow. He generated a massive amount of heat because not only did he have the ability to dissipate that heat through his blood so it wouldn't cause those enzymatic reactions to shut down, but then he had the ability to create sweat as a cooling mechanism. And that cooling mechanism, as long as he could generate sweat, as long as he could put that water on surface skin, even at 4 degrees or whatever it is in Green Bay in the middle of winter, he still generates so much heat. Another characteristic of water is its polarity. If you recall from our previous discussion, water is a polar molecule. We talked about polar molecules as being those molecules in which the covalently bonds were not shared equally. Water, they're not shared equally. I could go in great details to explain to you why, but take my word for it. Oxygen has a greater appeal for the electrons from hydrogen than hydrogen can attract the electron coming from the oxygen in that bonding relationship, as you can see from here on the picture. Now, what that results in, though, is it creates a molecule that is polar. We actually call this molecule dipole because it has regions of it that are positive charged and regions of it that are negatively charged. Now notice that what that allows for those weak hydrogen bonding interactions that we talked about earlier. Notice that one water molecule can have a hydrogen bonding interaction with 4 other water molecules. That's important because there's something unique about water that you might not have thought about before. Did you ever wonder why ice floats? Ice floats mainly because of that hydrogen bonding. Water is the only compound that when you freeze it, it doesn't shrink, but it expands, it gets larger. The hydrogen bonds prevent water from contracting as it freezes. The hydrogen bondings create lattice works as each water molecule interacts with 4 other water molecules. This causes the ice to be less dense than the liquid water, and thus ice floats. A neat concept to think about. It's hydrogen bonds that allow you to have ice that floats. Water also, by having this polarity, sets up an environment in which we can have biological colloids, in which we can take charged proteins, and we can submerge them here within the water molecules and protect them and move them through. This is called hydration layers or biological colloids. It also allows us to take other polar molecules, such as the sodiums and the chloride ions, the positive and negative charge ions, and keep them separated in solutions. Remember the concept of true solutions? It allows us to keep the positive and negative charged ions separated in these solutions, as you can see depicted here. Now, where's this relevant at? Anytime a negatively charged and positively charged ions come together, they will crystallize out and create salts. But remember one of the things about your salts, when placed in the water, that bond breaks and they are separated into their ions, their charged ions, which are important to us for electrical currents. If it worked for water's ability to keep the positive and negative charged ions separated, what would happen is we would have crystallization of these salts. And that occurs, if you think about it, when you think of things such as kidney stones. Other properties of water are important in its physiological reactivity, in which we will see hydrolysis and dehydration reactions occurring during the anabolic and the catabolic reactions in our body. And cushioning. We're going to see that water is going to be the key components of the fluids that are going to be encasing most of our organs to cut down on traumatic blows. Things such as cerebral spinal fluid, if you want to think about it. And finally, two other properties associated with water are the cohesive and adhesive properties associated with the hydrogen bonding. Cohesive would be water molecules interacting with other water molecules. Adhesive would be water molecules interacting with neighboring polar molecules other than water. Place I'd want you to go thinking about that is the serous membranes. Remember those double-layered serous membranes? Those double-layered serous membranes that enclose organs, such as this example here where you see the heart. Well, the innermost layer is going to be attached to the heart. It's known as the visceral pericardium in this case. And the outermost is going to be the parietal pericardium. It's going to be attached to neighboring organs. Now we have this double-layered membrane, but we have fluid in the middle of it, serous fluid, which is mostly water. And the role of the water is to make sure that we can position the heart in association with the neighboring organs, that it can have the ability to maneuver around as the heart beats. And we have that sliding, that frictionless environment. That's because water molecules, the cohesive characteristics allow water molecules to slide. But we have the adhesive as well because water molecules are also anchored to those two membranes. So ultimately, it's layers of water molecules that make sure that we hold the visceral pericardium to the parietal pericardium. It's that hydrogen bonding between those molecules, creating the surface tension in the middle and creating the adhesive characteristics on the side. On the flip side, if you want to think about it, adhesive is also how we get water to migrate up a tree. See these very tall trees in the forest, water is in the ground, obviously, comes in through the roots, but it has to be brought to the leaves for it to be used. How does it get there? It's the adhesive characteristics of water that allows it to associate with structures that it migrates up through, straw-like structures. Now it's time for you to step back and reflect a little bit. What is biochemistry? What's the difference between organic and inorganic compounds? And why is water the universal solvent? Next time around, we'll look at salts and acids and bases and pH. Have a great day. See you.